All right, last lecture before the Mathematica one, we solved for the potential outside of a conducting sphere, put in a constant external magnetic field. We solved this problem here. Okay, now let's do a little bit more with it. So this is the electric field. I plotted it in Mathematica, and I proved to you that it looked like we expect it to look like. Okay, so it is the right answer. Let's see if we can go a little bit further with it. Okay, so recall all this separation of variable stuff. It's solving Laplace's equation using boundary conditions and some particular math, a particular approach to the solution. Okay. We can do this with a variety of boundary conditions. If you remember right at the beginning of learning about solutions to Laplace's equations, we learned you can do it, you can do these solutions with V at some R, or you could use the gradient in the potential. So maybe for these spherical problems, a dV/dr, okay, at some R. Okay, so let's use the fact that we can also use the gradient of the potential to solve these problems. Okay, so what I'm going to do here is we are going to look for a solution, or rather, we're going to relate our solution to the surface charge, okay, which is sigma. And we can do that, if you guys remember, because the electric field outside minus the electric field in the perpendicular direction inside is related to our surface charge density, okay, our boundary value. And I could rewrite this because the electric field is related to the gradient of the potential. I could rewrite this as the potential at R equals A plus epsilon, where epsilon is just a wee bit, so you're just a little bit outside of the sphere, minus the gradient of the potential at R equals A minus epsilon. So you're just inside the sphere here. Okay, all of that is also equal to, in this case, negative sigma over epsilon naught. Okay. Okay, so if we have a conductor, which we do in this particular problem, I know that the gradient of our potential inside is going to be equal to 0. Okay, and that's because the electric field is equal to 0 inside of our conductor. Okay, so what does that leave us with? That just gives us the first term there, which is the gradient of the potential just outside our conductor is going to be equal to, right, what we just found for the potential. So that's the gradient of this guy. That was our external field plus our induced field. That's what we just solved for. Okay, this is all equal to, again, negative sigma over epsilon naught. When I take that derivative, I get that negative sigma over epsilon naught is going to be equal to negative E naught cosine of theta minus 2a to the third over r to the third E naught cosine of theta. But I want to evaluate this at r equals a. Okay, so this is at the surface. Okay. So if I want to figure out the surface charge density right at the surface, I'm going to plug R equals A into that, and that gives me that the surface charge density is going to be equal to positive epsilon naught times the cosine of theta. If I look at what I get here when I plug R equals A in, here, that simplifies it quite a bit, and I end up getting 1 plus 2, and I can't forget about my epsilon naught here. Okay, so I plugged A in for this, that canceled out, pulled out the common factor. Okay, so when I do that all together, that gives me 3 epsilon naught E naught times the cosine of theta. Okay, so we'll rewrite that one more time because I like writing. That's our surface charge density, and I like it because that is real simple, okay? Considering how complicated this problem could be.